okay, in which it will be the sources that can produce the electric charge intensity. Okay, so we're going to have a look on what kind of electrostatic charges that we have. Yeah, so reference for this topic, you can have it from Study Cool, the textbook with the given page numbers, yeah, from 112 to 128. Okay, motivation of this lecture basically is to familiarize the students with the type of sources that can be used in producing the electrostatic field. Yeah, right. So this will be the objective of this lecture number 3. We are hoping that by the end of this lecture, you must be able to calculate the total charge, yeah, for the given charge structure. Okay, means that if we give you any kind of charge structure, whether it is a line charge, whether it's a surface charge or volume charge distribution, you must be able to calculate this thing, yeah, which is the total charge of the given charge structure. Okay, so that should be the aim, the objective of this lecture, right? Okay, so let us proceed with next slide. Okay, basically, electrostatic charges will be having a Coulomb unit. Okay, Coulomb is the unit for charge or electric charge. And we have the smallest magnitude of charge, which is Q, of 1.602 times 10 negative 19. Okay, so that should be the smallest unit of charge, yeah? Right? And the unit is Coulomb, as mentioned before. This charge, it can be of positive or negative type. Yeah, we know that electric charges can be of positive and negative type of charges. Okay, and in general, we can see that the source of electrostatic field, yeah, the sources of electrostatic field can be in these 4 types or in these 4 forms. Yeah, in general, we have it in a form of point. We can have it in a form of line. We can have it in a form of surface, and we can have it in a form of volume. So these are 4 types of charges that we can have, yeah, that can be used in producing the electrostatic field. Yeah. Okay. So sorry, I have to go back to my Google Meet. This is the right. So I think I'm hoping that next time, please come early to class. Yeah, it'll make my life easier then. Okay then. So let's proceed with this slide. Right. So we're going to have a look on these 4 types of charges, starting from point charge up to volume charge. Yeah. Right. So for the point charge, this is considered to be the simplest charge type. Yeah. In which normally we label the charge to be Q. Yeah. Label it to be a Q. So we know that if we have just a point there, yeah, we just have a point Q. So it means that we are referring to the point charge. Yeah. And the unit for this point charge is in the units of Coulomb. Yeah, units of Coulomb. Right. And for next type of charge, which is called as a line charge. For the case of line charge, we are saying that the line charge is basically formed by point charges which are said to be accumulated on a single line or along a thin line. Okay, so we can see that we have a line. For example, this particular line here that we have here, for example, which is having a length from point of A to the point of B, the starting point and the end point, for example. So we can see that on this particular line, there are a lot of point charges which are said to be accumulated on this particular line charge or line structure. Yeah, so basically line charge is produced from a point charges, yeah, from a group of point charges, but in a form of line. Okay, so we can see like that, yeah. And if we have a point charge which is represented by a Q symbol, for the case of line charge, normally we represent the line charge to be in terms of rho L, which stand for the line charge density, yeah, line charge density, rho L. And the unit for this line charge density is coulombs per meter, yeah, coulombs per meter. So we have a line charge density for the case of this particular charge structure, and the unit of it, sorry, the symbol of it is rho L, and the unit is coulombs per meter because we are dealing with the line structure. Okay, so if we can have a look at this particular line charge structure, if we consider a small element, a small element of dl, because we have learned in our lecture last Monday that dl is basically a differential length, differential length. So let's say we have a length of L, for instance. We have a length of L for the line charge here from point A to point B. So a very small length of the line is defined to be a dl. And we can say that on this particular dl element, there exists a small amount of charge which is defined to be dq. Dq is called a small amount of charge that is located or that is resided in this particular small element of dl. So we can calculate the dq by simply multiplying the dl, the length, with the line charge density, because we know that dq is in coulombs unit, rho L is in coulombs per meter unit, and this dl is in meter. So when we multiply the rho L and dl, we're going to get the charge amount in coulomb. So this amount of charge dq is the charge that is said to be located, or that's said to be contained in this particular length of dl. Okay, so that should be the line charge element. So we can see that this is what we call as charge element. So dq equals to rho L dl is also known to be a charge element. So we call this as a charge element, or element of charge, either one. Okay, so we can actually calculate the total charge from the obtained dq here, because we know that from dq equals to rho L dl, so we can calculate the total charge of q, or I can just put it as qt, the total charge q, which are said to be contained inside this line charge structure of length AB by simply integrating the dq, in which this will give us integration of rho L dl, and basically we are integrating along the length of the line charge from point of A to the point of B. So that is how we define the total amount of charge inside this line charge structure. Okay, I hope it's clear on these the first two type of electric charge structure, point charge and the line charge. So allow me to go back to Google Meet, because there are students that wish to come into the class. Okay.
Doctor?
Yes.
I believe there's an option on Google Meet where you can make the admission automatically, or like you can emit the admission part, so you don't have to go back and forth. I'm not sure, but I remember one lecturer doing that thing.
Yes, I know that. That's why I want to actually make sure that you follow the time schedule, basically. Not simply you can just come in and come out like that. Okay, I hope you understand. Thank you very much. Thank you for your concern. Okay. All right, let's have a look on the third type of charge distribution. Okay, so we have the third one, which is a surface charge structure. So if we have for the previous case of line charge, where the charge are said to be accumulated on a line, for the case of surface charge, we can see that the charge are said to be accumulated on a surface. So just change the structure of line to a surface. Okay. So in terms of the characterization of the surface charge structure, we normally define the surface charge to be in the symbol of rho s. Rho s stands for the surface charge density. Okay, and the unit for this will be in coulombs per meter squared. Coulombs per meter squared. Right. So looking at this particular chart structure where we have the area, yeah, so we can see that this particular area of charge is said to be filled in with the charges, the point charges, all in this particular area, yeah, of the area of A. So we can see that if we consider a small area of ds, yeah, a small area of ds inside this area of A, okay, so we can see that inside this ds area, we can have a small amount of charge of dq, and this will be then defined to be equals to rho s ds, which is similar to what we have learned previously for the case of line charge, yeah. For the case of line charge previously, we have dq equals to rho L dl, and for the case of surface charge, it should be rho S ds. So this is also known to be a charge element, yeah, or element of charge for the case of surface charge structure. Okay. So the dq, I repeat again, dq is amount of charge that is said to be contained inside this ds element. So from here, we can then calculate the total charge inside this area of A by simply integrating the dq. So we can then have the total charge of inside this area of A by simply integrating the dq, which will be then equals to rho s ds. So that should be the integrations of the area of A basically. Yeah. So that's how we define the total charge for the given charge structure. Okay, so along the way, along the lectures, if you have any questions, you can just ask verbally, yeah, because I cannot see the chat from this presentation mode here. Right, so, and we come up with the fourth type of charge distribution, which is a volume charge. So previously we have a point, we have a line charge structure, then we have a surface charge structure, and the fourth one, the last one will be the volume charge distribution. So similarly, we can say that the volume charge distribution is formed by accumulation of point charges in a volume structure, yeah, in a volumetric structure. Okay, and we define the volume charge structure in the symbol of rho v, yeah, rho v stand for the volume charge density, yeah, volume charge density, rho v, and the unit for it will be coulombs per meter cube, yeah, because I have a volume. So coulombs per meter is for the line, coulomb per meter squared is for the surface, and coulombs per meter cube will be the volume, yeah. Right, so if we consider this volume charge structure, yeah, volumetric charge structure, if we have a small volume of dV, so we can see that the amount of charge dq that is said to be contained inside this dV element can be written to be rho v multiplied with dV, yeah, yeah, because rho v is in coulombs per meter cube, dV is in meter cube unit. So when we multiply these two parameters, we are going to get the charge in coulomb. So that charge in coulomb, which is a dq, basically will be charge that is said to be contained inside this dV element of charge. Right, so from here we can simply calculate the total charge, in which the total charge Qt for the given charge structure here will be simply integration of dq and integration of rho v dV, which is integrations towards the volume of the given problems. Yeah, so that's how we define the total charge for the given charge structure. Yeah, for the case of volume charge. So up to now we have understand that the electric charge intensity or the E field, electric field, can be produced, yeah, can be induced by four types of charge distribution or charge structure. We have the point charge, we have the line charge, we have the surface charge, and we have the volume charge. So these are four charge structure in general that we have that can produce or that can induce the electric field intensity. Okay, right. So let's have a look on the first example. So this example basically is to calculate the total charge for the given charge distribution and given volume. yeah, because we are requested to calculate the total charge for the given volume structure or volumetric structure, in which we are given here that the range of coordinate or the range of R is from 0 to 0.1, the phi is from 0 to pi, whereas the Z is from 2 to 4 with the given volume charge density rho V is R squared, Z squared sine 0.6 phi. This is to be in coulombs per meter cube unit, yeah, because we are dealing with the volume charge distribution. Okay, so we know that from the given coordinate here, R, phi, and Z, we are dealing with the cylindrical systems of coordinate. Yeah, so we have learned this in our class last Monday, that when we have R, phi, and Z, so these are basically related to cylindrical systems of coordinate. And from here, we can then calculate the total charge as requested from the questions, in which the total charge Q can be calculated by simply integrating the dq. And for the case of volume charge, the charge element dq will be equals to rho v dv. Yeah, this is for the given for the case of volume charge distribution. And we know that given that rho v is r squared sine 0.6 phi, that should be our rho v, and we need to define the dv. So for a case of cylindrical systems of coordinate, what should be the dv that shall be used here then? Can I ask Eric Julius? Eric Julius, yes, Eric Julius. Are you in my class? Eric Julius? Hello, Eric. Are you in my class now? Okay. Ali Abu Zaid. Are you in my class now?
Yes.
Yeah, okay, Ali. Can you please help me? Please define the dV for this given problems then.
R dr dz d theta.
Thank you very much, Ali. Okay, R, dr, dphi, dz. Thank you very much. Yeah, so it's very clear that this is the dV for a cylindrical system of coordinate. Well done, thank you. Okay, and from here we can proceed with integration. So that will be based on the triple integration because we are dealing with the volume. So we're going to have a integration of r power of 3 dr, integration of sine 0.6 phi dphi, integrations of dz. Okay, and we just put the range for this given problems where r will be having a range from 0 to 0.1, phi will be from 0 to pi, and z will be from 2 to 4. So we can proceed with the integration. So that will give us r power of 4 divided by 4, which will be from 0 to 0.1, and that will give us 1 over 0.6 negative cosine of 0.6 phi, okay, from 0 to pi, and then we're going to have z, which will be having a range from 2 to 4. Okay, so I left this for you to solve, yeah, because this is nothing much, just a simple algebraic representation or substitution. So that should be the total charge for the given problems in the units of Coulomb. Okay, yeah, so I hope that you understand on this particular example, very simple example, just to show how can we calculate the total charge from the given volume charge distribution and given space, yeah, or given coordinates, range of coordinates, yeah. In this case, we are having the cylindrical systems of coordinate. Okay then. All right. Thank you. So let us proceed with more examples. This is to be based on the study course book. Determine the total charge for the given for the following problems. Number one, we are having, okay, we're going to proceed with number one first. On line X from 0 to 5, if the rho L is 12x squared millicoulomb per meter. Okay, so this particular case, case number 1, we are dealing with the line charge distribution because we are having the rho L, and when we see the unit is confirmed that this is a line charge distribution, yeah, millicoulomb per meter, and the given charge is said to be located on this particular line of x from 0 to 5 meters. So if I can sketch the coordinate, because basically if we base on these given problems, we know that we are dealing with the Cartesian system, yeah. So all the time, please choose the suitable systems of coordinate for you to solve the given problems, yeah. So we have x, y, and z. So if you base on the problems, we can see that your line charge rho L is located on this particular line, which is from 0 to 5 of x. Yeah, so this is where your rho L is said to be located. Yeah, that should be the rho L of 12x squared, in which is having the black colored line. Yeah. Okay, so if you base on this, we can then define the dq, the charge element for the line charge. So we have learned before that for the line charge, the element of charge dq will be rho L dl. Yeah, and this will be equals to 12x squared. So what should be the dl to be used here then? Can I ask, sorry, I'm using the Telegram list, yeah? So I just call the name, Zul, sorry, I have to say, Zul Chipmang. Zul Chipmang, sorry lah ya, the name Zul Chipmang. Kenapa nama you Chipmang ya? Okay, Zul Chipmang, ada kat sini ke?
Yeah.
Okay. Zul
So,
Chipmang.
what is your question, Doctor?
Okay, what is the DL to be used here?
So, to be used here. Maybe we can use dx.
Thank you very much. Good. Yeah.
Is it correct, Doctor?
Yeah, it's correct. It's correct. Thank you very much. Because just to clear out, why is dx? Because your line is located on the x-axis. On the x-axis. So basically, we can choose a small element here on this axis, in which the dl here shall be equals to the dx. Okay. So thank you very much, Zul. Chipmang. Okay. Right. So we have dl.
Sorry, Doctor.
Thank you. Okay, so that's the dq, the charge element that we have here in this particular dl element. So from here, we can calculate the total charge, which is requested from the question. So q will be integration of dq, which will be the integrations of this 12x squared of dx. Okay, and if you base on this given axis, it should be having a range from 0 to 5. Yeah. Yeah, so we can have it as 12 of x power of 3 divided by 3, which is having a length from 0 to 5. So please substitute the value of 0 and 5 in this x value, and end up you're going to get the charge amount of Q in the units of millicoulomb. Okay, so that should be the answer for the first problem here. Okay, I hope I make it clear to you on the calculation of charge here and the selection of dl in this particular problems. Okay, so let me go back to the Google Meet. Okay. Muhammad Arifuddin ya yang bermasuk tadi. Muhammad Arifuddin.
Yes, Doctor.
Kenapa lambat dalam kelas?
Saya tertidur.
Masya Allah. Okay. Let us proceed with second questions here. We are given the cylindrical structure then, yeah? Cylindrical structure. We are having the radius of this cylinder is 3. The height is 0 to 4 meters. And we are given the rho s of Rz squared and a coulomb per meter squared. So we are dealing with the surface charge distribution. Okay, surface charge distribution. All right. So for this particular case, we know that for the surface charge structure, yeah, because we are dealing with surface charge distribution, so the dq for surface charge distribution should be equals to rho s ds. Okay, so this is charge element for the surface charge structure. Okay, I believe you have understand about these charge element for the case of surface charge distribution. But the issue now is which surface ds that we need to choose. Okay, which ds that we need to choose, because remember that what we have learned on Monday's class, that if we consider the structure of cylindrical system of coordinate, where if I can resketch the given box, okay, this box that we have seen, that we have learned in our class last Monday. Okay, so we have three different surfaces for the ds. Let me label this as surface A, surface B, and surface C. Okay, so this ds might be either one of these, whether it's surface A, surface B, or surface C. Okay, yeah? But you have to deal with the given problems here, the given conditions, that we need to find a charge on the cylinder with the constant radius of 3, but the height is having a range from 0 to 4. Okay then. Yeah, so we have a constant radius of 3, and the height of your cylinder is from 0 to 4. So in your opinion, which surface that suit the given problems here? Is it surface A, is it surface B, or is it surface C? Can I ask Marwan? Marwan, sorry, I'm sorry whether I'm pronouncing your name is correct or not. Marwan Diabes, is it correct? Marwan,
Yes, doctor.
Marwan Diabes, is it?
Marwan Davis, yes.
Diabes, okay. Marwan, can you please assist us which surface that need to be chosen then to satisfy the given problems here?
I think surface C.
Thank you very much. It's correct. Thank you. Yeah, thank you, Marwan, yeah, for your response. Very good. The reason why, because if we base on this particular structure, then A is having a varied radius. Yeah, radius is said to be varied. Yeah, so we have a dr. So it means that for the surface of A, the radius r is said to be varied. It's not constant. But we for the given problems, the r, the radius is constant all the time. So similarly, for the surface B, we can see that for surface B, the radius is also varied. Okay, so for that, it's clear that the correct surface to be chosen should be surface C. Thank you, Marwan, for your answer. So then we can have the dq for surface C. So I put it for surface C. The dq will be equals to rho s, which is given by rz squared in nanocoulomb unit, yeah, nanocoulomb per meter squared. That should be your rho s. And the ds for surface C, as what we have learned in our class last Monday. So let me recall, this is your r d phi, and that should be the dz. So when for the surface numbers for surface C, the area, the ds for surface C will be simply r d phi multiplied with dz. So that should be our ds, yeah, r d phi dz. Okay, so that should be the dq. And from here, we can then calculate the total charge q. Yeah, means that we are calculating the total charge on the curved surface, the curved surface of your cylinder. So if we can sketch a cylinder, okay, so this is your cylinder that we are dealing with, yeah, when which the radius is 3 and the height is from z equals to 0 to z equals to 4. So we want to find out what should be the amount of charge that is located on the surface of your cylinder. Yeah, because surface C is similar to this curved surface of the cylinder. Yeah. So for this, we need to integrate the dq, or integration of r squared z. Sorry, let me rearrange the equation then. Okay, so we are supposed to get r squared. Then we have d phi, and we have z squared dz. Okay, and from here we can take out the r outside because there is no integrand in this particular integration. So we have integrations of a d phi and integration of z squared dz. Okay, so we are given from the problems here that the r is 3, the radius is 3. So we have 3 squared, we simply substitute r equals to 3, and the phi, the d phi, the range of angle of phi. Okay, so we have defined in our class last Monday that for this particular case of cylinder, the maximum, the full cylinder, the full cylinder structure should be having a range of phi from 0 to 2 pi. So phi will be having a range from 0 to 2 pi. So that will give us, when we integrate this, we're going to have 2 pi straight away. And the z will be having a range from 0 to 4. So that should be z power of 3 divided by 4. Sorry, z divided by 3 divided by 3. Sorry, a mistake. It should be 3 down here. Okay, divided by 3. Okay, and that should be the integration from 0 to 4, and the unit for this integration. So please solve this on your own. It should be in Coulomb unit here. Okay, so I hope I make it clear on you on these particular problems. Yeah. Right.
Excuse me, doctor.
Yeah.
Can I ask a question?
Yeah, sure.
Doctor, I'm still confused. Why is it surface C, not B?
Okay, thank you for the question. So if we're referring to these problems, look at these examples here. They're given that radius r is 3. Yeah, radius r is 3, and z is from 0 to 4. If we choose surface B, surface B is here, we can see that for surface B, the radius is not constant, right? The radius is not constant for surface B, because surface B will be having the radius which will be varied in a dr range. So supposedly, if you want to, if you are requested to find the charge on the surface B, we are supposed to be given that the r should be having a range from some one point to another point. That's how it should be. But since we are dealing with a single point or single radius of r, so the best surface that suit this problem should be the surface C, because if we refer to surface C, the radius will be a uniform, constant radius value for surface C. Okay, I hope it's clear on this explanation. Yeah. Right. So let's have a look on part 3. Sorry, immediately so. Okay, for part 3, this is dealing with the sphere problem, spherical problems. Yeah, spherical problems. Within the sphere of r equals to 4 meter, if rho v of 10 over r sine theta coulombs per meter cube. Okay, so I think this should be very straightforward because we are dealing with the volume charge distribution. We are given the rho v here in this particular problem. Okay, so you know that for the case of volume charge distribution, the charge element dq shall be given by should be given by rho v dv. Yeah, that should be the charge element for the volume charge distribution. Yeah, dq shall be equals to rho v dv. Okay, this is for the case of volume, and we are given that rho v is 10 divided by r sine theta. That should be the rho v, and we need to choose the dv. So since the problem is given to be a spherical problem, so what should be the dv for spherical structure then? Can I ask Muhammad bin Said Toure? Muhammad bin Said Toure, correct? Muhammad bin Said, are you in my class?
Yes, doctor, I'm here.
Okay, thank you. Can you please assist me or assist us? What should be the dv to be used in this problem then? Sorry, Muhammad, I cannot hear you.
Sorry, doctor, did you say anything? I didn't hear.
Okay. Can you please assist us on these given problems? What should be the dv to be used in this equation here?
I still don't understand, doctor, so I can't really solve it at this point.
Is it the first class you entered?
No, it's my second one.
Okay. Have you do any revision for my first class last time?
I was there, but towards the end, I came at the middle.
Okay then. Okay, so kindly please refer back to the lecture notes, yeah, and also the videos on our class last Monday. Can I ask Sami Imat?
Yes.
Sami, yeah, okay, Sami, thank you. Okay,
R
Sami, can you please assist us? What should be the DV to be used here then?
RDR DVDZ.
Okay, that is for cylindrical structure then, Sami. If you have a spherical structure then, so what should be the DV?
I'm not sure, doctor.
Okay, thank you, Sami. No problems. Okay, so it's supposed to be R squared. Okay, dr, or I simply use it to be R squared sine theta. Okay, R squared sine theta dr d theta d phi. Okay, so if you forget about this, always refer back to this particular box that we have learned in class. Sorry, it's supposed to be, we have seen this block, yeah, in our class last Monday. It's for the spherical structure then. Okay, so that should be the dr. Okay, that should be r d theta, and this should be r sine theta d phi. Okay, so with these elements for each side, you can obtain the ds for respective surfaces, and also you can find the dv for this particular spherical structure, in which the dv is simply a multiplication of all of these elements, where when we calculate the dv, it should be r squared sine theta dr d theta d phi. Okay, right. So from here we can cancel few things here. We can cancel sine theta terms. We can cancel the r also. So we can have simply as tan of r dr d theta d phi for your dq. And subsequently from here we can calculate the total charge by simply integrating the dq, which will give us a tan integration of r dr, integrations of d theta, integrations of d phi. Okay, so in this particular problems, we are given that the sphere is having a radius of 4 meters. So simply we put the range of r to be from 0 to 4. For the theta and phi, because we are not given any conditions on the size or on the spherical range of theta and phi. Yeah. So what we can do here is that we assume that this particular structure is a full sphere. Yeah, full sphere means that the theta and phi, both of them will be in maximum range. Yeah, which means that the theta will be having a range from 0 to pi, and phi will be having a range from 0 to 2 pi. These are the maximum range for theta and phi. Unless if the question gives us some conditions on these theta and phi, for example, they give the conditions of hemisphere, for example. Yeah, hemisphere. So hemisphere, basically the theta and phi will be half. Yeah, so that should be the case. Right, so from here we can simply solve the problem straight away. So that we just proceed with the integration. So we're going to have tan, so that will be r squared over 2 from 0 to 4. That should be theta from 0 to pi, and then we have 2 pi from 0. Sorry, I apologize. So it should be phi, yeah, phi. Yes, phi from 0 to pi. So that should be your charge, magnitude, and the unit for this will be in Coulomb. Okay, right. Is that clear on this example? Right, I hope that's clear because in this example, we do it step by steps on the calculation of the total charge with the given charge distribution. We have the line, we have the surface, and we have the volume charge distributions. Yeah. Right. So this is also related to the sphere structure. If based on these problems, we are given the rho v. So I can see that this is similar to what we have seen in the previous example, the third example just now. So I won't be doing this example because that will be similar in terms of solving this question. So I think you can solve this on your own. Yeah. Again, just as a hint, the dq will be simply as a rho v dv. Yeah, so we have dv given here, which is 2 times 10 power negative 3 r squared cosine squared phi over sine of theta. The dv, it's a sphere structure. So again, The dV will be r squared sine theta, the r, the theta, the phi. Okay, you can cancel out all of this. Sine theta and sine theta can be cancelled out. And finally, we can find the total charge Q by simply integrating the rho v dV or integrating this particular amount or equations. Yeah. Right. So I think I make it clear on this calculation of charge amount for the given rho v and the given radius, the given size of a sphere. Yeah. All right. So that's the end of lecture number 3. So I hope that by now you have you can fulfill you can fulfill the required objective or the requested objective, in which by any given structures of the charge distribution, whether it's a line, whether it's a surface or a volume charge distribution, you must be able to obtain the total charge amount of the given distribution structure. Yeah. So basically, if you base on the given examples and given solutions just now, the fundamental things, the important things will be on the coordinate system. Yeah, as I mentioned before in our class last Monday, you need to have a good grip on these coordinate systems, basically on the DL, on the DS, and on the DV, because that will be used again and again in this EMT course. Yeah. Right. So let us proceed with this lecture number 4. In which you are going to start on the Coulomb's law, basically on the electric field intensity calculation. So in lecture number 3, just now we have learned about 4 types of electric field source: the point, the line, the surface, and the volume. So for lecture 4, after this, we're going to see how this particular charge distribution can produce the electric field intensity. Okay? All right. So this will be lecture 4. Wait then. Okay, so let's have a look on lecture number 4. This will be the topics to be learned. The first one will be on the introduction, a very short introduction to the electric field intensity. And number 2, we're going to start our lecture on Coulomb's law. But for lecture 4, as I mentioned before, we're going to learn or going to apply the Coulomb's law for the first charge structure, which is for the point of charge. So for the line, the surface, and the volume, that will be learned in our class next week, inshallah. Yeah. Okay, reference for this lecture number 4, still on the same page of 112 to 128. Okay, and motivation for this lecture number 4 is that we want the student to understand well on the concept of electric field intensity and the method of its calculation. Okay, so you must be able to calculate the induced electric field intensity if you are given the field structure or charge structure, sorry. Okay, so this will be the objective of this lecture number 4. By the end of this lecture, you must be able to apply Coulomb's law in calculating electric field intensity due to point charge. Okay, I stress here, just due to point charge only. Yeah, and then number 2, you must be able to calculate the electric force induced by the point charge. So, as I mentioned, our aim for this lecture 4 is just on the point charge. So number 1 is to calculate the electric field intensity, and number 2 is to calculate the electric force, because for the case of Coulomb's law, the field intensity and the electric force are interrelated. Yeah, so we're going to see after this. Yeah. Okay, so this is a very short introduction on electric field intensity or electrostatic field intensity. Okay, so basically the word electrostatic composed of 2 different words there. We have electric field and also the static source. That's why we have the words electrostatic field intensity. The static source, why static source? Because we have learned just now that 4 types of charges The field, the line, the surface, and the volume, all of them are static. It's not moving at all. Yeah, that's why we call this as a static source or static field, I can say. Okay, so normally we are representing the electric field intensity as a vector of E. Yeah, a vector of E. A vector of E will represent the electric field intensity. Yeah, electric field intensity, and the unit for this E field is a volt per meter. Yeah, volt per meter. Okay, so I hope that you understand the E field intensity. It comes from the words electrostatic. Why static? Because the source is static. Okay, and for now we are going to cover. We're going to use the first law that can be applied in calculating the electric field intensity, which is a Coulomb's law. Okay, Coulomb's law. Okay, so Coulomb's law is basically developed by a French scientist, Mr. Coulomb. Yeah, Mr. Coulomb. So this law is named after him, Mr. Coulomb. He said that the magnitude of electrostatic force between 2 point electric charges is directly proportional to the product of magnitudes of each charge and inversely proportional to the square of the distance between the charges. Okay, this is the quote by Coulomb's, yeah, the Coulomb's law. Okay, mathematically it's given by this equation, the force, okay, the word electric force there, yeah, electrostatic force. So based on that, we can see that the Coulomb's law initially is invented or produced, used to calculate the Coulomb's law. Sorry, used to calculate the force, yeah, electric force. So the electric force that is produced between the 2 point charges, yeah, can be calculated, in which it is proportional to the charge amount. The Q1 and Q2 is the charge amount or charge magnitude, and this particular force is inversely proportional to the square of the distance between the charges. So it means that if we have 2 point charges, for instance, we have Q1 here, we have Q2 here. These are two charges that are separated by a distance of R, for instance. Yeah, we have a distance of R between the 2 point charges Q1 and Q2. So the electric force between these 2 point charges can be calculated by using this equation. The magnitude of the charge, so the magnitude of the force, yeah, magnitude of the force is equals to or proportional to the magnitude of both charges Q1 and Q2, and inverse proportional to the square of the distance between the charges. Okay, so this is based on this Coulomb's law. So based on the experiment done by Mr. Coulomb, this in proportional sign can be then changed into equation sign or equal sign, where we have F shall be then equals to Q1 Q2 divided by R squared, in which what he did is that he add a constant of K. Yeah, so the proportional sign is then changed into the equal sign, but need to add the K. K is a constant. Yeah, K is a constant, and based on the experiment done by Mr. Coulomb, he found out that the K basically is equals to these parameters, where K is equals to 1 over 4 pi epsilon naught, in which epsilon naught is known to be a permittivity in free space. Yeah, permittivity in free space, because this is the assumptions made by Coulomb, in which he assumed that the environment, the medium that he was considered at that particular time is just a free space or a vacuum environment. Yeah, vacuum environment. So permittivity, what is meant by permittivity? Permittivity is the behavior of the electric field in that particular medium. Yeah, behavior of electric field in that particular medium. Yeah, that's why we have the word permit. That, yeah, permit. Yeah, permit means that it able to pass through the medium. Yeah, so permittivity for the electric field in the free space is defined by this constant of epsilon naught, which is defined to be 8.854 times 10 of negative 12 in the units of farad per meter. Okay, so later on in chapter 5, you're going to see some changes, some changes on this permittivity when we are dealing with the dielectric material. So we're going to see some changes on this permittivity values. Okay, so for now, up to chapter 4, our medium that we consider is only a free space or vacuum medium. Yeah. Okay, so for that, if I can rewrite the K in this particular unit or in this particular equation, so we can have that the F shall be equals to 1 over 4 pi epsilon naught. We have Q1, Q2 divided by R squared. And in terms of the vector, we can add a vector here, and this will be unit vector of R. Okay, so what's meant by this unit vector of R? So for that, we need to refer to these figures on top here, where we have two charges Q1 and Q2. Okay, so we are supposed to have two conditions. The first condition is that when the Q1 is said to exert a force on the Q2. Okay, so look at the arrow here. The charge of Q1 is said to exert the arrows into charge of Q2. So this is defined to be the force of F, the force of F, which is equals to 1 over 4 pi epsilon naught Q1 Q2 over R squared, and unit vector of R is directed from charge of Q1 to the charge of Q2. So I use the R in the subscript of 1 to 2, which means the unit vectors is directed from 1 to 2. Okay, yeah. So this is the force that is exerted. Yeah, that's exerted, or I can say that is produced by charge of Q1 towards the charge of Q2. Okay, we can also have a conditions whereby the force will be exerted by the charge of Q2 to the charge of Q1. Look at the arrows here. So that should be the case whereby the force will be equals to 1 over 4 pi epsilon naught Q1 Q2 over R squared, and the R will be having a subscript from 2 to 1, which meant that your unit vector is directed from Q2 charge to Q1 charge. Okay, so basically, if we base on this, the amount of magnitude for the force will be similar, yeah? Q1, Q2, we have both equations, got Q1 and Q2, and we also have R squared as the magnitude. But the difference will be on the unit vector. The direction of unit vector will be opposite. Okay, so that should be the force exertion due to 2 point charges. Okay, I hope it's clear on this calculation of electric force. Yeah, electric force in which initially Coulomb's law is designed or is used to calculate the electric force between 2 point charges. Okay. All right, so let us proceed then from the understanding on the force or electric force from the Coulomb's law. We can then apply this concept in calculating the electric field intensity. Yeah, in calculating the electric field intensity. Okay, so let us redefine or reuse the concept of electric force that we have learned previously. So we have, let me repeat, yeah. So we have a charge of Q1 here. We have a charge of Q2 here, and we can say that if we assume that the force is applied or the force is exerted from charge of Q1 to the charge of Q2, so the arrow should be in this direction, yeah. So the force now will be from Q1 to Q2, so we can write that the force F shall be equals to 1 over 4 pi epsilon naught Q1 Q2 divided by R squared, okay, in which the distance between these two charge is R. Yeah? Let me sketch for you. That should be R in terms of the distance. And from here, the unit vector will be from R, will be from 1 to 2. So that we're going to have this unit vector, which is directed from charge Q1 to charge Q2. Okay, so from this equation, if for instance, yeah, I delete the charge of Q2. The same point, but we assume that there is no charge at this particular point, yeah. So for that particular case, what we can say is that the charge Q2 is said to be brought to the left-hand side, in which these equations now becomes F, or the force divided by charge of Q2 will be then equals to 1 over 4 pi epsilon naught Q1 over R squared, and the direction will be the same, which is from point of 1 to the point of 2. So I redefine this to be point number 2, yeah? So we have a point number 1 and point number 2. Okay, so this F divided by Q, is defined to be the electric field intensity of E. Yeah, force per unit charge. So we define this to be electric field intensity of E, and from this equation we can rewrite the equation here to be Q1 over 4 pi epsilon naught R squared new vector of R from 1 to 2, which means that based on these equations that we have successfully formulated the equations here in the rectangular rectangular line here, we can say that the E field can be calculated. The E field induced by a single point charge can be calculated if we know the distance from the point charge to the intended location, and we know the unit vector from the point charge to this intended location. Okay, in other words, I can say that if I have my charge here, for instance, I have my charge Q, I have this point, let's say point A, I have point B, okay, I have point C. So by using this equation, I can say that if I have a charge Q, point charge Q, I can calculate the electric field induced at this particular point of A. Okay, let's say the distance between this charge Q and the point of A is RA, for instance, and in the vector is RA, for instance, in the vector of RA. So I can say that at A, the electric field that will be produced at the point of A, okay, at the point of A, the electric field that will be produced at the point of A will be Q divided by 4 pi epsilon naught RA squared, and having the vector of RA. So that should be the electric field that will be induced at the point of A. Similarly, at the point of B, okay, let's say the point of B here is having, sorry, not very nice using the yellow color. I think you should use the green color then. Okay, that should be the RB. The distance is RB. Yeah, distance is RB between Q, charge Q and point B. And the unit vector directed from Q to B, from charge Q to point B will be RB unit vector. So at B, at the point of B, we can then calculate, or we can say that the induced electric field intensity at the point of B will be Q over 4 pi epsilon naught RB squared, and the direction of unit vector of RB. Okay? And the same things apply for the charge C, in which I can just write here that at C, the electric field, I can just put here E, yeah, E vector, EA, I can say EA is the E field at point A. This is EB, which is electric field at the point of B, and EC is electric field at the point of C, will be Q over 4 pi epsilon naught RC squared and RC unit vector, in which we can see that the distance here is RC, and the vector from Q to point of C will be RC hat. Okay, so that should be the case. Okay, I hope it's clear on this explanation on migration from the concept of electric force to the concept of electric field intensity. So in case if we have more than one point charge, for instance, yeah, if I can, sorry for that. Okay, if for example, yeah, we have a single point, yeah, you have a single point. Okay, let's say I have a point A here. So I have 2 point charges. Let's say this is my Q1 and this is my Q2. So Q1 will be having, let's say, the distance from Q1 to point A is R1, and the distance from Q2 to point A is R2, for instance. And both charge will be having or will be having their own unit vector to the point of A. Let us put this to be R1 hat, and that should be the R2 hat. Okay, so that should be unit vector from both point charges, Q1 and Q2 to the point of A. So from here, I can say that my electric field intensity at the point of A, which will be induced by these 2 point charges, shall be then equal to the summation of each electric field induced effect, which means that at A, I'm going to have a summation of 2 electric field intensity terms, in which we are going to have the first one, which is due to Q1, for instance, Q1 over 4 pi epsilon naught R1 squared with the R1 hat. That should be the first electric field intensity terms, and we need to add this with the second contribution of E field, which is from the charge of Q2, which will be Q2 over 4 pi epsilon naught of R2 squared with the R2 hat. So that should be the concept, the principle of superposition. So I need to write here, that's what we call as a principle of superposition, in which we need to add the effect of electric field produced by all point charges that we have in the given problems. Okay. All right. So I hope I make it clear on these issues on the Coulomb's law, migration from the force to the electric field intensity. Okay. So I don't have to proceed with this slide. We have discussed this in the previous slide just now. Right, so let's have a look on this example. Number 1. We are having a point charges, 2 point charges, having a magnitude of 5 microcoulomb and negative 4 microcoulomb placed at given coordinate 321 and negative 406. So if we look at this particular example, we know that this is dealing with the Cartesian, Cartesian or rectangular systems of coordinates. Okay. So let's have a look and let's sketch the problem. So we have Q1, which is 5 microcoulomb, located at 3, 2, 1. And then we have the second charge, which is located at, this is Q2 of negative 4 microcoulomb, located at negative 406. So the question is determine the force on Q1. Yeah, obtain the force on Q1. So that should be the line connecting the 2 points there. So the force on Q1 means that your force must be directed from Q2 to Q1. That should be the direction of the force. Yeah, because you want to find the force on Q1. So the vectors of force should be directed from this particular point of Q2 to the point of Q1. Yeah. Okay, so from here, I can write the force in a vector form, in which a force, yeah, this should be the vector, should be equals to Q1, Q2, based on the equation of force that we have learned before, divided by 4 pi epsilon naught. Okay, and that should be R squared, and that should be in a vector of R. Okay, that should be the equation that we need to use. But I prefer to use the vectors instead of using unit vector form, in which I can rewrite this unit vector to be in terms of the vector R over the magnitude of R. Okay, in this particular case, we are assuming that the r, small letter of r is similar to capital letter of R. Okay, this is our assumption here. So if we substitute in the vector of R, which is in terms of the vector over the magnitude, so we can have the equation, or we can rewrite the equation to be Q1, Q2 over 4 pi epsilon naught, the vector of R over R power of 3. It's similar things, yeah? It's similar things. Right. So from here, we need to define what should be the R vector first. And from the R vector, you can find the magnitude of R. Okay, so basically from here, the vector should be in this direction. That should be the R vector, directed from Q2 to Q1. So from what we have learned in our vector revision last Monday, so R vector shall be equals to the point or the coordinate of Q1 minus the coordinate of Q2, which will give us 7 of x, okay, plus 2 of y minus 5 of z. Okay, that should be our vector of R. Okay, I hope you are clear about this. And from this vector of R, I can straight away find the magnitude of R by simply square all the vectors components. So that should be 49 plus 4 plus 25, and up you are going to have 53 plus 25 will be set of 78. Okay, so we have both terms then. We have the vector, we have the magnitude. So that should be substituted into the force equation here. So we have then F should be 5 microcoulomb multiply with 4 microcoulomb, which are the magnitude for the Q1 and Q2, which is a negative sign there for the Q2, divided by 4 pi epsilon naught. We have the R vector, which is 7 of x plus 2 of y minus 5 of z, divided by the magnitude power of 3. So that should give us 78 to the power of 3 over 2. Okay, so that should be your force. And that should be having units of Newton. Yeah, that should be having units of Newton, yeah, because we are finding the force in this particular case. Right, so the rest, I hope that you can solve that. Yeah, you need to simplify the equation, knowing that for this particular cases, we are dealing with the Cartesian system of coordinate. So the force will be having a component of x, component of y vectors, and component of z. Okay, any question for the first problems here so far? I hope it's clear, yeah, on explanation on this example number 1 on the force. Okay, so let's have a look on this example number 2. So we are given a charge of negative 0.3 microcoulomb located at A of 25, negative 30, and 15 in centimeter, and a second charge of 0.5 microcoulomb located at the point of B, negative 10, 8, and 12 centimeter. The question is find the E field intensity. So I just use E field, yeah? E field intensity at A at the origin and B at the point of 15, 20, and 50. Okay, this is the case whereby we are having more than one point charge that will produce the electric field or the E field intensity, yeah? Okay, so let's sketch the diagram, the problem. So we have the first point is at A, 25, negative 30, 15. So this is in centimeter, yeah? So basically, when we solve the equation, we need to write it in meter, in SI unit. And then the charge is negative 0.3 microcoulomb. Secondly, we have the charge located at B, having a coordinate of 10, negative 10, 8, and 12 centimeter. And the charge is 0.5 microcoulomb. And the point of interest for the first case is at origin. So I just put it as at origin. Okay, this is at origin. So be at 0, 0, 0. So basically from here, we are supposed to have two different values of E field. The first one shall be produced by charge of A, yeah, charge at point of A. Let's say we define this as EA, Yeah, EA is the electric field produced by a charge. And then we have the second electric field produced by the charge at point B. So I just use EB to define the electric field intensity that will be produced there. Okay, so from here we can see that the total E produced shall be equals to electric field A plus electric field B. Yeah, so we put this at origin. Yeah, so at origin, we can see that the total E field will be EA plus EB. Okay, so from here, we need to find one by one what is EA and what is EB. So for EA, okay, we have learned before in the previous slide that it should be the charge of negative 0.3 microcoulomb, which is the charge amount, yeah, this one, divided by 4 pi epsilon naught. Okay, so I'm now using the R capital, yeah, instead of R small r, I'm using R capital for the vectors. Instead of in the vector, I'm using vectors, so it should be R vectors. I put RA over RA power of 3. Okay, so the vectors of RA basically should be these vectors lah. That should be the vectors of RA lah. Yeah, the vectors directed from the point of A to the point of origin. Okay, so let me clear the, make it clear on this use of the vectors. Okay, just to make sure that you understand this clearly. So basically from previous, we have E field is Q over 4 pi epsilon naught. We have in the vector of R, and we have R squared, remember? But what we have done for the case of force just now, I'm using this in the vector of R as vector of R over R magnitude, R magnitude. And we assume that R and R capital are the same things. And basically from here, we have the Q over 4 pi epsilon, the vector of R over R power of 3. That's why we have this equation here, yeah? Okay, and then the EB, okay, the EB, okay, let me solve this one first. So we have negative 0.3 macro, okay, and RA is the vectors from this A to origin, so we can have it to be equals to negative 0.25 direction of X. Yeah, I'm using meter now. Yeah, this is in centimeter, so I'm using meter. So negative 0.25 of X plus 0.3 of Y and minus 0.15 of Z. Sorry, I don't have enough space there. Divided by 4 pi epsilon naught, and the RA magnitude, yeah, we can have it to be 0.25 squared plus 0.3 squared plus 0.15 squared, and that should be to the power of 3 divided by 2. Okay, that should be your electric field A, yeah, which is produced by electric field by the charge at the point of A. Okay, similarly, for the charge at the point of B, we can write it as follows, where we have the EB. Yeah, the EB shall be written to be 0.5 microcoulomb divided by 4 pi epsilon naught. Then we have the RB vectors over the RB power 3 over 2, in which RB is this vector. Okay, in which from here, you can see that RB vector can be calculated to be the origin, the point here minus the B point. So that will give us 0.1 of X minus 0.08 of Y minus 0.12 of Z. That should be the vector of RB, yeah? And divided by 4 pi epsilon naught. So RB will be equals to 0.1 squared, 0.08 squared, 0.12 squared to the power of 3 over 2. Okay, so that should be the E field produced by a charge located at point B. So end up, what you have to do is that you need to add the electric field produced by EA, or produced by the charge at point A, and the electric field produced by the charge at point B. So need to add them together, yeah? So addition of the vectors should be the addition with respect to the same vector components. I think you understand this very well, yeah? And for the case of part B, in which the point now is changed from origin to 15, 20, and 50, in which we have we need to change now the final location. The intended location is now changed to another point, which is a point of 15, 20, and 50. So basically, the idea should be the same. Yeah, the difference will be on the production or the produced vectors. So RA and RB, the vectors will be changed. Yeah, because we have different point here. Previously is origin. So when we change the final point, the RA and RB should be changed also. And for that, the magnitude of RB and magnitude of RA should also change as well. Okay, so I think you don't have to do this. You can try this on your own, but nothing much here because we just changed the final point. Okay, any questions for this example so far? No, yeah. So bear in mind that the unit for the E field must be always returned in your answer, which will be in volt per meter. Okay, then let's have a look on this example. We are having case problems whereby there are 2-point charges, the Q1 and Q2, located at different position, located at 403 and 201. Okay, so let us sketch the problems. We have Q1 located at point of 40, -3. Then we have Q2, which is 4 nanocoulomb, located at the point of 201. Okay, so these are the location of 2-point charges, yeah, Q1 and given 4 nanocoulomb as a Q2. The question is, find the charge of Q1. Need to find this charge of Q1 such that the electric field at 506 has no Z component. Electric field at 506 has no Z component. So let us, let us roughly put the point of 506 to be here. That should be 506, yeah, the intended location. So electric field at 506 has no Z component. So before we can consider the effect of Z component, you need to find out what should be the electric field at 506 first. Okay, so based on this, we know that the electric field should be contributed by 2-point charges, Q1 and also the 4 nanocoulomb charge. So for that, we can have 2 electric field lined. The first one is from Q1, second one is from 4 nanocoulomb. So let me use a vector of R1 here, and here should be the vector of R2. Yeah, just to differentiate the vectors for both electric field intensity values. Yeah, okay. So from here we can see that the total electric field, I just write it here, total electric field that will be produced at 506. So I put here at 506. Okay, the total electric field will be equals to Q1, which is unknown, divided by 4 pi epsilon naught. So R1 vector, you can calculate this from the initial point to the end point. So 5 minus 4, okay, that should be X direction. There should be no Y contribution because 0 minus 0 will be 0. And then for the Z, that should be 9Z. Okay, that should be the vector of R1. And then for the R1 magnitude, that should be 1 squared plus 9 squared power to 3 over 2. Okay, so that should be the contribution of electric field by a charge of Q1 to the point of 506. Okay, similarly, a contribution from 4 nanocoulomb to the same location or the same point will be 4 nano, okay, divided by 4 pi epsilon naught. And the vector of R2, you can have it as 5 minus 2, which is 3 of X no contribution for the y, and for the z will be 5 of z. So that should be the vector of R2. And for the magnitude, yeah, it should be 3 squared plus 5 squared to the power of 3 over 2. Okay, so let us be clear on this equation. Yeah, I'm using this equation here where we have E field equals to Q over 4 pi epsilon naught, the vector of R over R power of 3. Yeah, R power of 3. And because this is a magnitude, supposedly that should be square root of 1 squared plus 9 squared. That's why we have it as 3 to the power of 2. Sorry, power to the power of 3 over 2. Okay then, yeah? I hope I make it clear on these issues, yeah? So now we can then use this given information here, which say that we need to find the Q1 such that the electric field at 506 has no Z component. Okay, if we base on the equation that we have obtained here, the final results that we have obtained here, we can see that at 506, the total electric field that will be produced will consist of two components, which are the component of X and the component of Z. Yeah, because when we add them together, we are going to have the X component that should be added and also the Z component that can be added. Am I right? Yeah, we have two components, the X component, which is in the red color, and the Z component, which is in the orange color. Okay, so we have two components there, yeah, the X component and the Z component. But the question state that, or the questions given give us that the E field at 506 has no Z component. So for that particular case, we can see that the Z component, I can put EZ here, which stands for the Z component, will be equals to 0. Yeah, EZ here stands for the Z component of the E field, yeah? So that should be 0, in which if we base on this equation, we can write it as 9 of Q1, which is from the first terms, yeah, the first term here, that should be 9 of Q1 divided by 4 pi epsilon naught, 82 to the power of 3 over 2. Okay, so that should be the Z component for the first term. And for the second term, the Z component is given by 20 nano. Yeah, 4 nano times 5 will be 20 nano over 4 pi epsilon naught, 25 plus 9 will be 34, 34 to the power of 3 over 2. So this is epsilon naught. Yeah? And the results, the summation of these two terms here, which are the Z component value, will be equals to 0. Okay, we add the Z components only. And from this equation, we can then simplify these equations there, in which we can cancel out few things, and we can cancel out the 4 pi epsilon naught straight away, in which finally we're going to have the Q1 shall be equals to negative 20 nano multiply with 82 to the power of 3 over 2 divided by 9 multiply with 34 to the power of 3 over 2. So that should be the amount of charge that you should that shall be obtained if we consider that the Z component for the total E field at 506 is 0. Okay, so that should be the charge amount Q1 in Coulomb unit. Okay then, any question on this solution so far? I hope the explanation is clear, yeah? Okay then, so there's no, yeah, soalan.
So
Any
we just
question?
need to exclude the X part, right?
Correct.
Alright, okay.
Right. Okay then, proceed with the second part of the questions here. Because the question asks us about the force. Okay, this is about the same question, but the difference between the first and the second one is that the first one is related to the electric field, whereas for the second one is related to the force. Yeah, the force. Yeah, for the force, given that the force on a test charge at 506 has no x component. Yeah, test charge. Test charge is what? 1 coulomb. Test charge is a charge with the amount of 1 coulomb. Right. So basically, there's nothing much difference here because 1 coulomb doesn't give us any significant changes on the equation. We just change the parameters from the electric field to the force, total force. Okay, but 1 coulomb should be no effect because basically if you base on the equation, let me write the equation for you. The F will be Q1 Q2 over 4 pi epsilon naught R vector over R power of 3. If we substitute, if let's say you want to find the force on 1 coulomb charge, yeah, so either Q1 or Q2, that in this particular case, let's assume that Q2 is 1 coulomb. So that should be 1 coulomb. Yeah, so if we substitute this 1 coulomb into Q2, basically there should be no changes on the equation here. Yeah, on this equation, there should be no changes because 1 coulomb does not give any significant changes. So we just change the equation from electric field to the force. Yeah. All right. So this particular case, it's mentioned that for this time, the force at 506 has no x component. Yeah, has no x component. So that should be another round, another methods of calculating the Q1. Previously, for the first part, we are using the z component terms, but for the part B, we are using the x component terms because it's mentioned that the force has no x component. So for that, I just put that the fx stands for the component of x for the force shall be equals to 0. And from this equation, for the first part of the equation, you're going to have for the x component, it should be Q1 over 4 pi epsilon naught 82 to the power of 3 over 2. And the force on the x component by the second component, yeah, second equation here should be equals to 12 nano, yeah, because 4 nano times 3 will be 12 nano divided by 4 pi epsilon naught, and that should be equals to 34 to the power of 3 over 2, and this shall be equals to 0. So again, and up we can find out the Q1 straight away. These terms can be cancelled out. So finally, we can find the Q1 shall be equals to negative 12 nano divided by 34. Sorry, this should be 82 times 3 power of 3 over 2 divided by 34 to the power of 3 over 2. So that should be the Q1 that calculated based on the assumption that the force on the test charge at 506 has no x component. Okay. Any questions so far?
Doctor,
Yeah.
I'm still confused. How we can use the same formula with the E for the force?
Okay.
Alright.
Right. Let us rewrite the equation. Yeah. Let me write the equation then. Okay. For the force equation, if we can recall back, I have to sketch the diagram then. Okay. So we have these two things. Yeah. Q1 and the charge of 1 coulomb. So basically, from the equation of force, we have F. Yeah. Force on 1 coulomb. Yeah. Force from Q1 to 1 coulomb. So we have Q1 multiply with 1 coulomb divided by 4 pi epsilon naught factor of R over R power of 3. Okay, so that should be the equation for the force from the charge of Q1 to the 1 coulomb charge. Similarly, okay, I've total, yeah, this is total F on the 1 coulomb charge plus the force due to 4 nanocoulomb to 1 coulomb charge. So we can write it as 4 nanocoulomb multiply with 1 coulomb charge divided by 4 pi epsilon naught R2 vectors over R2 power of 3. So this should be R1 vector, sorry. That should be R1 power of 3. Okay, so this is the force. Yeah, this is the force exerted by both charge Q1 and charge 4 nanocoulomb to the point of 1 coulomb. So 1 coulomb equals to 1, right? So we can see that this is similar to the equation of E field. E field total just now is Q1 over 4 pi epsilon naught R1 vector over R1 power of 3 plus 4 nano over 4 pi epsilon naught R2 vector over R2 power of 3. This is the equation for the total electric field at 0.506. This is the force on 1 Coulomb charge at 506. So 1 Coulomb charge here does not give any significant effect. So basically, the equation for the force and electric field intensity will be the same. Because 1 Coulomb doesn't give any effect. Unless if the charge is 2 Coulomb, then you're going to have different things then. I hope it's clear, yeah?
Alright, so we just use 1 Coulomb for the test charge, right?
Correct. For test charge, it's always 1 Coulomb.
Alright.
Right.
Okay, thank you.
Thank you very much for the answers for the questions. Yeah, hopefully we'll have others also. Okay, that's for the end of lecture number 4. Alhamdulillah, we have done the Coulomb's law. So just to recap, lecture 4, we have learned about the Coulomb's law. Basically, Coulomb's law initially is used to calculate the electric force, the Coulomb's law. And from this idea, we have then migrate. Yeah, we use this idea to migrate in calculating the electric field intensity. Okay, and for what we have done so far, we have calculated the electric field intensity and the electric force due to point charge. Yeah, due to point charge. So I hope that's clear on these issues. So inshallah next week on Monday, we're going to proceed with the calculation of electric field intensity due to other charge distribution on the line, due to surface, and due to volume charge structure, because that is considered to be a continuous charge distribution. Okay then. Any question before we